Hello, I'm Robert, and I'm working on this article and wondering what I'm going to do about it, but I thought I'd just talk through it a bit. So this is about how NASA it's proposing that it's going to redefine large parts of Mars as being like the Moon for planetary protection. And what I want to say in this article is that Mars is not known to be sterile anywhere yet. And it can't solve its planetary protection dilemmas by just redefining Mars as like the Moon. So, and I've been interested in science and astrobiology for a long time. I'm a science blogger in my spare time at Science 2.0, and I write often on planetary protection. And then I wrote this book, which as far as I know is the first popular article, only the second article for the general public about planetary protection. And it's called Touch Mars ? And the only earlier one I know about is called When Biospheres Collide. That one is free to read online. And this is as well, When Biospheres Collide, a history of NASA's planetary protection programs. So that is mainly historical and focused on NASA, and mine is rather broader and is looking at all the current prospects and the future. This is, of course, a bit about the future. It's connected to the past, connected to the future, and look very much a much broader way at planetary protection. It's often past, you're getting a chapter in a book, but as far as I know, it's the first, and there are plenty of specialised, like the Mars sample return studies, like they're like small books in themselves. But these, and loads of papers, of course, but I don't know of another actual complete book on the subject. So this is what this report has made, the commissioned a report, and the report recommended that NASA should reconsider that much of Mars' surface could be Category 2. That means the same classification as the Moon. That means that you can land human beings anywhere in that part of Mars without taking any precautions except to document what you've done, and that you can return samples from there back to Earth. It doesn't actually say that, but that would be unrestricted Category 5, and if it was Category 2, you would expect it to be unrestricted Category 5 for the sample return, that you can return it from anywhere. And this is very timely, because first of all we have the private space with Elon Musk being very optimistic, but of course he's always optimistic with Elon time it's called, where he's very optimistic that humans are going to be heading off to Mars in mid-2020s. I don't think they will myself, because it's so far away. It's so dangerous, very dangerous. Not just it's like, and Chris Hadfield, former commander of the ISS, he says that to head off to Mars at this stage would be like some people who are paddling around in the Seine in Paris with little canoes. And they say, hey, we've got a canoe, we can paddle in the river, so let's head off to Australia. So that's a very experienced astronaut, and in his mind, then that's what heading off to Mars would be like, to do it just now. And the reason being that as soon as you leave Earth orbit, then you are committed, just as the Apollo 13 was committed to go around the Moon. Soon after, they did have a chance to get back, but the best way back was around the Moon. Well, you'd be committed to go all the way around Mars, which is about 2 years away. And imagine the Apollo 13 astronauts. Something goes wrong, like with them, with their carbon dioxide, with the life support, some chemical problem, some problem with the fire. And then they've got 2 years in which they've got to survive before they can get back to Earth. So that's why it's so dangerous to go to Mars at this stage, until we've got spacecraft that are astonishingly reliable. If you can take one of Elon Musk's spaceships and put it on the far side of the Moon, and just sit the crew there for 2 years studying the Moon without any supply from Earth, then you are getting to the point where you probably want to send in a Armada of 3 to be safe before. And I don't see us being able to do that next decade. And probably, like Chris Hadfield says, it'll be the next generation, like the people who are just being born now. Would likely be the ones that could possibly go off to Mars orbit. So anyway, so I don't think it's so urgent as NASA seem to think in the forward direction, and then in the backwards direction, then it is very urgent for NASA because they are sending a mission to Mars in 2020, which is going to cache rocks, which they hope to return to Earth before 2030. But so that may be what's kind of driving this, at least as much as the private space thing. And so I'm going to explain why why this is actually not going to make any difference to the planetary protection in the backwards direction, because they don't seem to be aware of how things have changed since Apollo. At the time of Apollo, all there was were these categories 1, 2, 3, 4, 5, and the Outer Space Treaty to protect Earth from life returned from the Moon. So back at the time of Apollo, then Carl Sagan had this idea of a way that there could be life on the lunar surface, about a meter or two below the surface. It's not that different from some ideas for how there could be life on Mars today. He had a published paper about it, a couple of published papers actually, and so at the time of Apollo, they knew that that the Moon was pretty much a vacuum, but they still had this very faint possibility that there could be life well below the surface, and there could be spores of that on the surface which could get into the lunar dust. And so, this biosphere collides. They look into all this, and they look about what actually happened. And I had no idea, being as just an ordinary person, back then I had absolutely no idea about planetary protection. And when I watched the Apollo 11 landing and they landed in the sea, as a keen, young, I was in my teens, and I watching it land, and thinking, oh, how wonderful it is. They come back from the Moon, and I saw the quarantine facility, and they got in the quarantine for 2 weeks, and I just assumed, never even gave it any thought that they were protecting Earth by doing that. But actually, if you look at it with the kind of lens of history, and knowing what we know now, and even back then, Carl Sagan was absolutely appalled about how they tried, about what they did, because he was very keen on planetary protection. And what he saw with his eye of someone who knows about these things was that, the very first breach happened. So you need to know that as the... before I go any further, for any of you who are scared, then I need to explain to you that we are very well protected, and that's my whole point in explaining this. We are very well protected today. NASA don't realise how well we are protected. But back then we weren't. Legally we were very well protected now. But back then we weren't. All we had was the Outer Space Treaty, which just been signed a little while, not so many years before, and that is mainly focused on weapons in space and not building a military base on the Moon. It's the reason why the Apollo didn't land and say we claim the Moon for the United States. We said we're coming for all mankind. It's mainly because of the Outer Space Treaty, which prohibited a nation on Earth taking parts of the Moon and other places in space as being their territory, and prohibits setting... obviously military personnel can go to the Moon. The Apollo people were military personnel, but they can't go there in a military capacity, and that's not permitted. So we can't set up a military base on the Moon. So that's what happened. So the Outer Space Treaty focuses on all that stuff, but it has very little. It only just has a few phrases on protecting. It's called harmful contamination and protecting Earth from the Moon. And there was no legislation about how you do that. And NASA actually, it's actually rather grey area whether they were legally permitted to do it this way. They didn't go through any legal process. They just worked out amongst themselves what their guidelines would be for a return sample from the Moon, and they published these guidelines on the day that Apollo 11 launched to the Moon. That's all detailed in this book, and this meant that nobody else outside of NASA even got to read it before the Apollo 11 mission. And then even this thing that they had, or at least officially read it, and then this so it was woefully inadequate. Even if people of the day had read it, they would have said, you can't do it that way, most likely. And so then when they returned the samples from the Moon, then they actually made an executive decision to make it even weaker than this plan that nobody had even scrutinised. And they were originally going to lift the command module out of the sea onto the ship and then get them out of the command module on deck rather than. But instead, what they did is they got them out of the command module in the sea. Now you need to know that when the astronauts went out on the lunar surface, they tracked in a lot of the lunar dust with them, and they could smell it like gunpowder. It was everywhere inside, very, very dusty inside. There's no doubt at all. When the divers went in with their big dinghies and they opened the command module door and they threw in the decontamination suits, which the astronauts then put on. Of course, some dust came out and got into the sea, the worst place to contaminate at that point. And actually, it was an earlier stage when the command module vented some of the air on the way down, and that would have got some dust into the atmosphere and down into the ocean. And then, when they came out in the decontamination suits, then the divers swabbed them down with permanganate solution, and then dropped the swabs into the ocean. Because back then, they apparently believed that swabbing someone with permanganate would decontaminate them of lunar microbes. So this did nothing. And after that, it was all a formality. And the 2 weeks in the quarantine, then there's no reason why even rabies it's now considered to be longer than 2 weeks before you'd have to quarantine them from. And things like leprosy, then you're talking about decades. It's not feasible to contain leprosy with quarantine. So, and how you know what this microbe and what it could do to the human body and whether it could do it just straight away. And some people say, but an extraterrestrial microbe could do nothing to a human body. But we have Legionnaire's disease, and that Legionnaire's disease is able to use the same methods it does to as a disease of biofilms, as a disease of the human lungs, which looks like a nice warm biofilm to it. And so maybe I should do that. So that's the background. And so we got these. This is obviously not written by astrobiologists. It's written by geologists, and they said that NASA should reconsider. There should be Category 2 versus Category 4, because their latest site is 2014, but most of this is even early, 4, 5, 6, 7. They're supported. They say that's 1983, 2008. 1969 and 1984, and that's the latest site is 2008. And so I'm just going to go forward a bit, and go back and forth a bit. So since 2008, there's been a huge reappraisal of the habitability of the Martian surface, and these documents, I say, don't describe Mars as it is today. And this is one of the discoveries. I need to save this page so that I can play the video. Just a minute. So, right. So this is Nilton Reno, and he was a PI for the Phoenix mission, principal investigator, and he runs the Mars weather station on Mars on Curiosity, and he's probably an acknowledged expert on water on Mars, liquid water on Mars. And he's written a review article, which I think is the only big review article on liquid water on Mars that covers all the different possible habitats. And since 2008, then there have been more possible habitats have been discovered have been proposed, or even indirect evidence for them, than there have been years since then. And there have been more forms of life many more forms of Earth life that could live in those habitats have been postulated than there have been years since 2008. So by stopping in 2008, they have stopped just before the most interesting point in astrobiology for Mars for decades. And now I just want to talk from 148 onwards. I go to 148. This is a discovery he made. He noticed, he was one of the first to suggest liquid water on Mars. Phoenix did this made remarkable discovery. It landed at the lunar poles, and it discovered from the isotope ratio of carbon and dioxide, just the isotopes of carbon, the isotopes ratio of oxygen, minimal information. Then it came to the conclusion that Mars has been producing carbon dioxide recently in the geological recent past, and that the oxygen in the carbon dioxide has exchanged with liquid on the surface, chemically exchanged. And from that, then they concluded there must be liquid water on the Martian surface. The main question was whether it's sporadic or there all the time. And since then, we've had many discoveries and that suggest that they actually make it pretty clear that there is liquid water on Mars and pretty much everywhere for at least a few hours every year. And this is one way. If you've got salt and ice, which covers a large part of Mars but not the equatorial regions, and this is one way. And when Phoenix Lander landed, salt was thrown up on its legs, and this salt, maybe mixed up with ice, then formed little droplets that then merged and then fell. But we don't know for sure that even it was salt or it was ice, because there was no way that Phoenix could actually measure. It didn't have instruments that could reach to its legs and measure what this actually was. So we are left with hypotheses. So he is now, I've got to look at, with this Mars simulation chamber, then his team worked out, this simulates the Mars surface in there, and this is at University of Michigan, and it simulates all the it's very difficult to simulate because Mars is extremely cold. I need to explain that. It's got half the light that Earth has, but that radiation doesn't mean that you go like so from 20 degrees to 10 C or something like that. It means that this is to warm it up from its natural temperature, which is not so far above absolute zero as due to the internal heat of Mars. You've got to warm that all the way up, and it's got half the radiation to warm it up, and so it gets very, very cold there at night. It goes down to minus 70 degrees C, and below it actually gets much colder than minus 80 something, even in the equatorial regions, because you get dry ice comes out, and that's just on the surface of Mars. You get that cold, and then in the daytime it can go right up to our huge temperature swings. We don't have anything like that with these huge temperature swings on Earth. Not such big swings as that. Not in just one day. So it's quite hard to simulate it, and with the very low atmospheric pressures. Anyway, so they did this experiment simulating salt on, and let's 148 onwards. I'll just play this. His discovery of his team. If I find 148, 144, that'll do.
In a few hours, we don't see the formation of liquid. If we have ice and then the salt on top of the ice, in a few tens of minutes, liquid water forms. Our measurements clearly.
And that's if there's anywhere on Mars there's salt, salt is thrown up on top of ice, which may have explained these Phoenix droplets.
Indicate that, and it's really a proof that the liquid water form at the conditions of the Phoenix landing site when the salt is in contact with the ice. Based on the results of our live experiment, we expect the soft ice that can liquefy perhaps a few days per year, perhaps a few hours per day, almost anywhere on Mars. So going from mid-latitudes all the way to the polar region. These are small amount of liquid water. But for a bacteria, that will be a big swimming pool. A little droplet of water is a huge amount of water for a bacteria, right? So small amount of water is enough for you to create conditions necessary for Mars to be habitable today. And we believe that this is possible in the shallow subsurface and even the surface of Mars polar region for a few hours per day during the spring.
So
Mars.
And obviously this report that NASA is relying on, they seem to be completely unaware of that research. And especially if you go a bit further or maybe they do, but they sort of think that they're convinced that this life can't get so close to the equator because of the lack of ice. But I mean, if humans are going to Mars, they're going to want ice. They're going to be looking for some source of water, so it's very difficult to see. But anyway, so a bit more about that. So there's actually another source of vines, another source of, as I said, there have been more potential habitats like that one. I would call that just one potential habitat, these droplets of salt and ice. There have been more of those suggestions and sometimes indirect discoveries than there have been years since 2008. And this is another one. That this was in Curiosity, it discovered that liquid vines from delicate salts. You may know that salt, if you have a very damp atmosphere, then ordinary table salt becomes kind of sticky. And if you have the kind of clumps and it's difficult for it to pour, well, if you have on Mars, then you have these perchlorates. They don't have the chlorides like they have on Earth. They have perchlorates, which is very oxygenated chlorine, chlorides that mix a lot of oxygen into the chemical formula, and you get these perchlorates. You also get sulfates instead of sulfides. So it's very oxygenated there, the vines. In a lot of oxygen in the chemical formula. It's rather like also the very surface of the Mars is red, it's very rusty, like this iron with lots of oxygen in it. And there actually is oxygen in the Mars atmosphere. And a recent discovery by Vladislav Semenkovich, they came to the conclusion that actually water on the surface of Mars, this is only a recent discovery, that's a very recent discovery last autumn, that there should be actually significant amount of oxygen even in the most difficult places for oxygen to get into it. Once it reaches equilibrium, then it will be enough oxygen for aerobes, for oxygen breathing microbes, which is quite a striking discovery. And this so anyway, so these those vines you find, they might just possibly, depending how fast you can get in, then they might even be oxygen rich as well. And so anyway, they discovered that these liquid vines that form wherever Curiosity drives over the sand dunes, then that the air is above it is drier than it should be, and then when they leave the sandy areas, the humidity increases. So something in the sand dunes is taking up water vapor from the air, and rather a lot of it. And they found out that at night it must be taking up so much water is being taken out of the air that it's driving over, that there must be something under there that is actually producing liquid vines. And really a significant amount of liquid is being drawn out of the atmosphere every night over the sand dunes, but not over the rocky areas. And but it is extremely cold at night. It goes down to this. We're talking about below minus 70 degrees centigrade in the wintry conditions, in local winter. Then you get these vines that are plenty of water for life, but they're very, very cold. Now, Earth life doesn't actually have a hard limit in the direction of cold. It does in the direction of saltiness, but in the direction of cold, it's got a very soft limit because a fair number of Earth microbes are able to withstand going very, very cold by turning a kind of glass inside, a glassy liquid without any sharp crystals. And you actually get very slow metabolic processes even when it's in this glassy state. Just very, very slow motion. And then as it gets colder and colder, below minus 20 degrees C, while it's still liquid inside, then you certainly have metabolic processes going on, but very slowly. And it's a big question at what point is the lowest temperature at which it can actually replicate. And this is all extremely hard to study in the laboratory. You can't do it by just counting them, because when it gets well below minus 20 degrees centigrade, you get it replicating every century, and then eventually they think possibly every 1,000 years and longer. So it's possible that life can continue to replicate even at very low temperatures, but over extremely long timescales. But when it comes to planetary protection for Mars, then the way they handle this is they say, well, okay, it could be it does replicate, we just don't know, well below -20, but if we introduce Earth microbes to Mars, and it's not going to replicate for 1,000 years, then we don't need to worry about that. So that's how they handle that with Mars planetary protection. And that's why they say that if the binds go below -20, then we can treat that as being safe for Earth life. It doesn't actually really mean that Earth life can't get into it, but it could get into it and it just wouldn't reproduce for thousands of years. So, and so they found that as the day continued, the binds warm up, but then it becomes too dry and too salty for life. And that's in the top fives. They could have permanently hydrated binds below about 15 centimeters below the surface, and they would never get warm enough for metabolic activity. So that would be top temperatures of -40. So when you get down to 15 degrees centigrade, it's -40. When it's the top 5 centimeters, it gets warm enough for Earth life, but it dries out too much. Now, but what if Martian life is able it's probably got perchlorates inside, and be quite natural since there aren't any normal salts and lots of perchlorates, and it works as an antifreeze, lots of perchlorates in its environment. And if any life has evolved to be able to survive, then on Mars, if there is life on Mars, it's very likely evolved if it's at all possible for life to survive in these conditions. These conditions hardly occur on Earth. But on Mars, and certainly not below -70, something like that, below -40. So but on Mars, it would be a very strong premium for any life that can actually survive in these conditions. And it could do it by having faster metabolic processes than Earth life, which, if it warms up, might be quite devastating for it. But so there's this paper about I forget its name of the paper, but it's by Schultz Macook, the famous astrobiologist. And I'm sorry, names I know very well sometimes go out of my mind, and I've always been like that. It's not really a senior moment. I've always been a bit like that. And anyway, so there could be ways that life would form that life would be able to survive on Martian life. It's a little bit faster, and then there'd be a big question of whether life would also survive at higher temperatures, but it would have a strong premium to be able to survive this very big temperature swing. So maybe it does find a way, because it's got these huge temperature swings between day and night. So maybe Martian life is better able to do that whole thing. And we have plenty of Earth microbes that, for instance, are adapted to be able to survive in hydrothermal vents and also survive in the human belly button, to take one example. So we do. So it's entirely possible you've got an extremophile that can also survive in the Earth temperatures. So now what could happen, and this is something Milton Reno thought of. Now I'm not clear from this quote whether he's thinking about Earth life doing it all by itself, or whether this liquid vine would have Martian biofilms in it. He says, life as we know it needs liquid water to survive. While the new study interprets Curiosity's results to show that microorganisms from Earth would not be able to survive and replicate in the subsurface of Mars, Renaud sees the findings as inconclusive. He points to biofilms, colonies of tiny organisms that can make their own microenvironment. So it doesn't say whether those are in this mention of him. It doesn't say whether these biofilms are of Martian life or of Earth life. But if it's Martian life, then it could be surviving at night at -70 degrees centigrade, and in the day it keeps the warmth up to habitable temperatures well above 20 degrees centigrade in the top 5 centimeters or so. And so then the Martian life, as long as it can survive at night, and if it can still be there in the daytime, they can have these nice fast metabolic processes. And so now you wouldn't notice that from the surface, that you wouldn't be able to know if there's any biofilms, and Curiosity can't dig even down 5 centimeters, so it's got no way of knowing if there's anything there. And so these binds, they mightn't become too salty for Earth life in the daytime. So this then gives you both. It gives a way that could be Mars life there, even where Curiosity is, and there could be biofilms there that Earth life could contaminate. So for them to say so conclusively, back there where they said that various scientific studies suggest the survival and application of terrestrial biota are unlikely on the Martian surface, well, we don't even know that where Curiosity is. The various other ways, I just thought this one particularly striking, and because it does it both ways, then this could be one way that it happens. There are also the recurring slope lineae, and there's the ideas of micropores in salt pillars. There's Gilbert Levin's idea, and these are all things that could be happening where Curiosity is. There's a possibility of that for some times of the year you have these frosts on the surface, and this actually the dry ice comes out onto the surface, and then ice gets in it, and then when that melts, then these current equatorial regions, I'm not sure, I haven't actually seen photographs of frosts where Curiosity is, but you certainly get them in the equatorial regions. And then as these melt, then it would form a moist air layer above the surface, which life might be able to exploit. And it could be that it takes a while for it to spread out into the atmosphere. There are the recurring slope lineae. Nobody is quite sure what the conditions are there, and the various other ones. So there are a fair number of potential habitats, even where Curiosity is, although it's considered as amongst the least likely places for life on Mars. But you can't rule it out yet. So then you might wonder, well, what does it matter if we bring Earth life to Mars? I mean, what does it matter if we're going to be bringing life everywhere? So some people think that it's almost our duty to take life wherever we go, and some people are rather askance at that and think, well, no, we make so many mistakes on Earth, taking life from here and there. Is really like the right thing to do before we know what we're doing? Well, certainly it's whatever your views are about the eventual end outcome of whether we should try and replace other biospheres by Earth life as we spread out in the universe, or whether we should be respectful of it, then certainly we want to find out what's there. We want to know what's there before we do whatever we do to it. And so this little story that I wrote, little news items, that you can imagine, the first, and this is to explain why we need to be careful in the forward direction. So the first astronauts on Mars, and by Robert, I'm just pretending I'm the reporter, the first astronauts land on Mars, plant flags in the soil. And just for fun, I've done the flag of the Earth. It would be kind of nice if we had a unified mission. It's so expensive, it would be more likely to be even, hopefully maybe China involved, Russia and Europe and US, and maybe just possibly, unlike Apollo, they would have a flag of the Earth. Anyway, so there they are, and as a young child, I would just be, oh wonderful, this would be just great if they do that. So I would never had a thought about planetary protection until it took a long time to realise that it's an issue. So then we have that, and everybody's cheering, and I'd be saying how wonderful it is. Then they say, Mars astronauts find life. And all except the specialists like Carl Sagan or whatever, and the current equivalents, they'd be looking and say, oh, wonderful, wonderful, they found life there, clear life, they found the clear signs of life on Mars. This is what we're there to look for. And they find it in these recurring slope lineae. But then, big disappointment, the Mars life was from Earth. Oh, it turns out that the life was a salt-loving microbe that sneaked in on the spaceship. And the astrobiologists wouldn't be too surprised on that, because we found loads and loads of different microbes now that would be very likely would actually be very happy in Martian conditions. But it's not so, not sure if the general public is so aware of that. And it could have blown there in a dust storm. So you get a lot of people saying, oh, the Mars surface, any life on Mars is not going to spread on Mars because of all the UV light. The atmosphere doesn't block UV light like it does on Earth. And it's very sterilising. Never mind, nevertheless though, what they call very sterilising, they used to think it would just be seconds, as if your microbe just falling off a suit into the ground would be sterile by the time it got there. We now know that some microbes can withstand hours of the Martian surface conditions in full UV before they're killed. And then what you need to be aware of is that UV light is blocked out even by a few millimeters of dust and by a shadow. So it fell into a footprint, and an astronaut stood on that footprint within an hour, say a few hours, it would be protected. If it got into a shadow of a wheel or on the ground and some just dropped something on top of it, it's protected. And then but easier just in the shadow. Generally, would like to be covered in boulders, and in the shadow of a boulder, or just on the shady side, or underneath the spacecraft. And then you have loads of dust storms. This is an image of imagining a dust storm with astronauts facing it. And every few years, you get these dust storms that spread and cover the entire planet. And the dust would travel hundreds of miles a day at the speed of the winds in these dust storms. And dust storms block out the sun almost completely. 99% of direct sunlight will be blocked out. And the individual microbes, a spore that gets into the dust, it would be protected by the iron oxide in the dust itself as well. If you got into a little crack in the dust, and this was an idea that goes back to Carl Sagan, he talks about how a microbe embedded in a dust grain could be spread anywhere over Mars. And then he does a calculation of how long it would take, which is only a decade or so, if the surface of Mars was like Earth, and microbes could reproduce like Earth life. Of course, both of those are not true, but if you reproduce much slower than Earth life, I think every month or something, then within a decade, then it's got the same population as the Earth's soil, something like that. So obviously, it's not. We don't have conditions there like Earth's soil, but we have all these little habitats, and we have the dust that could take a microbe from one habitat to another, and so you can see from that way of thinking, that it's not absolutely clear once you've got microbes spreading around in the dust and going hundreds of miles a day, and at night, of course, there's no UV at night, so if it's spread at night, there's certainly going to be no UV, and that can damage it if it's spread in a dust storm at night. And I'm not sure. In this story, then it's quite often happened that one of our spacecraft has landed on Mars in the middle of one of these dust storms. So that could easily happen to the humans. And then there's a big dust storm that covers over the entire planet, and the days turn to night for weeks, and they can't see anything because they're just in the dust. And so I imagine this story that this happened soon after they got to Mars, just like has happened with some of our robots that get there. And this then took the dust to this nearby RSL, and that's how it got contaminated. So now I imagine a little bit later, this sort of up again. They actually found the Martian life. They found native life, and they found it probably by drilling below the surface, below the contaminated area, and they found this RNA life it's got ribosines, and it's very much smaller than a ribosome, involved with the replication, and it's got the RNA, but it hasn't got any DNA, because Earth life is RNA and DNA, and it's DNA that carries the thing from one life, that carries that our genes are encoded in, and the RNA is used to transfer that and to make it into mainly to make proteins and things. They just have no DNA, no ribosomes, which is a huge big molecule involved in replication, and no proteins. And astrobiologists generally think that there must be something much simpler than modern Earth life, because it's impossible to imagine all this complexity just suddenly arising in one go. With 10,000 different chemicals, suddenly you come together in just the right mix and all simultaneously in the right place. Indeed, we can't make, even if we tried, we can't make a modern Earth cell, even the smallest modern Earth cell, we can't make it from basic chemicals. The only way that we can produce life is by taking previously existing life and modifying it. If you were to try to make even the simplest cell by just putting things together, we could make virus things, but that's not really a living cell. It depends on the cell to kind of look into. And to make an actually living cell, then that could kind of scavenge its material from the environment and so on, then it has to, as soon as you start mixing the chemicals together that would make up that cell, they'd react to each other, and you wouldn't have anything there. You can't just build it up like sort of brick, like Lego bricks. It doesn't work. So we have no way to make even if we could figure out and knew exactly all the chemicals that were involved in early RNA life and how it works together and how it all reacts and so on, we couldn't make an early RNA world cell. And the people who are trying to find out what early life was like, what they're trying to do is to evolve it, trying to give it a little helping hand in the direction of evolving very quickly. They're trying to do very fast evolution with helping hand from early cells. They haven't had any success with that yet, but there are people who are trying that. And so if we found RNA world life on Mars, it would be amazingly interesting. And you get these Mars colonization enthusiasts who say, whatever we find on Mars, it's going to be Earth life. Well, to start with, and it's got to be Earth life that's got there from Earth. Well, to start with, there could be a shadow biosphere, which is like RNA world life on Earth. There was a search for a shadow biosphere on Earth, and we haven't found it. So there obviously is that possibility that there could be a shadow biosphere on Mars, if there could be on Earth. So even if there was Earth life there, depending on what Earth life has got there, then it might well be that the RNA world life is still there. And it might be, but it doesn't seem to exist anymore on Earth. There have been lots of searches, and they haven't found it, this early life. But if it is still there on Mars, it might be that whatever destroyed it on Earth, we destroy it on Mars if we bring that life to Mars. So it could even be that there's Earth life there and a shadow biosphere of RNA world life, and that the RNA world life there could go extinct if we bring Earth life, and more microbes there. That's one possibility. But another possibility is that Earth life has never got from Earth to Mars. So the thing is that if you go back to the Chicxulub impact, when of the dinosaurs, that was the last time that any life could have been sent from Earth to Mars, because it has to leave Earth at the escape velocity of 11 kilometers per second. And to get through the Earth's atmosphere, leaving it, it's got to be leaving the atmosphere at 11 kilometers per second, which means it's going through the atmosphere faster than the fireballs that you see where they've slowed down and they start turning into a fireball in our atmosphere. They'd be a lot slower than these rocks would be as they go out of our atmosphere. So you're talking about life that's, as it leaves our atmosphere, it's a great fireball and ionizing plasma which go through little cracks into the interior. So it's going to be thoroughly sterilized on the outside. And these rocks, they have a very sudden shock of exchange as the asteroid hits the surface and a bit gets thrown off at this 11 kilometers per second, very suddenly 11 kilometers per second. And this is a really huge asteroid in which you have a kind of area where it sort of moves, it changes its acceleration more slowly as it goes up into space. And the larger the asteroid, the more you have such a region which could make it kind of cushion it more. Like very early, before 3 billion years ago, when you had 120 kilometers, 30 kilometer asteroids, and the very early ones, 100 kilometer asteroids, they're easier for them to send viable life into space. And so, anyway, with the shock of impact, it would destroy most Earth life, and maybe most of it anyway, almost certainly all photosynthetic life. You're talking about an impact into a shallow tropical ocean, which is not the most likely thing to send life to Mars, that would survive on Mars. And then once it gets to Mars, then all the bits that's left are going to the vacuum of space, cosmic radiation as well. Most likely, most of it takes, well, it would still be arriving there millions of years later, probably 20 million years later. And some of it would get there in the first century, and some even maybe within decades. But it would still be quite a bit sterilized by cosmic radiation. It gets to the surface, and anything that's been there for a long time, if you sterilize all the way through, and that's a huge, huge, huge rock. In fact, I don't think the Chicxulub impact, it would be more like meter-sized scale rocks. It couldn't really make sense, the really big ones, into space. And then once it gets to Mars, then it's got to try and find these habitats there. And the life, even if it lands in this, for instance, it lands in the Curiosity website, a Curiosity landing site near there, but the brines outside are minus 70 degrees centigrade, and the rocks inside are, I mean, assuming that it doesn't have these biofilms, or the biofilms don't make it very habitable for Earth life, then in that case, then the brines outside are minus 70 degrees centigrade, and or they're too salty, and the life is inside the rock, and the surface of the rock has been sterilized by cosmic radiation, and it's been sterilized by heat. And if you've had the shock of impact and the shock of hitting Mars and a fireball again as it comes into the Mars atmosphere, it's by no means certain that any Earth life has got to Mars. In the very early solar system, as I said, it's much easier, but how robust was that very early life, and would it have got there and survived? So astrobiologists, when they look at Mars and when they design experiments to look for life on Mars, they do not assume that it is related to Earth life. They try to find ways to search for any form of life on Mars. So we have no idea, and it could be that all there is there is, for instance, an early RNA world life, because because it had ceased very early on when there was early life, and since then you can argue both ways. Maybe the adverse conditions since then have led to rapid evolution, or maybe they have led to life that has hardly evolved at all. So that's one of the possibilities there. And that would be very easily made extinct. And then, so this is the extremely sad story, that the astronauts regret making Mars life extinct. Its experts say it is too late to do anything about the introduced Earth life on Mars, since the dust storms will spread their spores and don't microbes throughout the planet. The astronauts say that they regret making native Mars life extinct. And can we do anything to protect at least some of the RNA world life on Mars? So far, there's been no success in getting it to replicate in the laboratory. I think that this is a not impossible future news story about Mars. So we need to think, what kind of future are we headed for? This is why we protect Mars. And this bit about there being no success in getting to replicate in the laboratory. I mean, if they've only just found it and they've got a few samples, then it's got contaminated and they can't get any more, and they just got this little sample of a few bits of RNA world life that is still that is still alive, but it mightn't actually replicate, or it might start replicating a bit, but they can't keep it going, and it sort of stops, it sort of peters out. And I mean, that's not impossible. It's very difficult to replicate some microbes, Earth microbes, because they can't figure out what the conditions are and exactly to replicate it in the laboratory. So a lot of people don't realise that. I've just come down here. I've got a picture which I might pop in at some point. So this is the human microbiome, and you could say that is one of the most studied of the microbiomes we have, and this is and this particular study of the human gut, and people have tried very hard to grow the microbes we find in the human gut, but an awful lot of them you can't grow. We still don't know quite how to get them to grow in a laboratory, even though they're perfectly happy in the human gut. And then the many that haven't been detected yet, and the ones where you can find these fragments of genes, but you can't actually figure out what life form it came from. And then the genes that with the genes, 40% of genes, they don't have any match in functional databases, so they have no idea what the genes do. And that's just the human gut. So so why was I talking about that? Let's go back up. I've lost track. So yes, so those are very difficult. So that's life even in the human gut. Then it can be difficult to replicate it in the laboratory. And now we've got a completely unknown life form that's from RNA world life. We've never studied RNA world life before, so it's not too surprising if there's no success in getting it to replicate in the laboratory, even though it's absolutely fine on the Martian surface in the Martian conditions, and in a little club with other RNA world life forms on the surface, and with the chemical history of what the habitat it is that it's been in. So that is a distinct possibility. that we find RNA world life and then it's extinct. It would be so sad. And then here we have 50 years after the astronauts accidentally introduced Earth life and made native RNA world extinct. We look back at the mistakes. How was it that we didn't see this coming? And also look at the many attempts since then to try to reverse contamination of Mars, and these often made the problem worse. And that's like the Lascaux caves. I use this parallel in my Touch Mars question book, that they had huge issues trying to keep it free of mould in the early 21st century, and sometimes their attempts to make it to reverse the mould actually made things worse rather than better. So it's quite difficult once you've introduced something. So, and now, so that's in the forward direction. That's why we have to be very careful in the forward direction. Now we have very little legislation to protect us. All we have in the forward direction is the Outer Space Treaty, and this only says harmful contamination. There's a big, long legal discussion. What does harmful mean? What does the word harmful mean in that phrase, harmful contamination? And the general conclusion of the lawyers who look at that is it means that it certainly includes being harmful to the other experiments of other nations. So if you follow that, then you would say that NASA would be harming the experiments of, for instance, ESA and Roscosmos, and the Russians and the Europeans and the Chinese and the Japanese and the Indians. They'd be harming their experiments by introducing Earth life to Mars, and by making native Mars life extinct, if that was to happen. So there's a reasoning arguing there that it is harmful to others and not just to your own space program, and that is basically a legal basis on which on planetary protection in the forward direction. That's all the law we have. There's no other law to protect except this little phrase in the Outer Space Treaty that we have to prevent harmful contamination. And the lawyers argue about what the rest of it means, because there are a few other phrases that it's not clear how they work together with each other, about how the different phrases in the Outer Space Treaty work with each other. And there's one lawyer, this is definitely an outlier position, a lawyer called Laura Montgomery, who's often cited by the space colonization side of this debate, and she argues that if Elon Musk was to launch to Mars and to want to land humans on Mars, then in the forward direction, the United States agrees they definitely have an obligation to tell everyone else that a private space company from the United States is in the process of doing something which will harm their experiments on Mars, has the potential to harm their experiments on Mars. But she says there's no legal obligation for them to tell him to stop. Other lawyers say that there is legal obligation and that you have to actually actively act to prevent your citizens from harming Mars. Now this is a very specific thing that happens. I think it's partly taking account of the rather unusual way that legal systems work in the United States, which is different from the way you could do it in the UK. I'm not sure you could apply Laura Montgomery's argument to if there's a mission launched from the UK. I'm not sure you would be able to apply it, because she's using local domestic law mixed up with international law to come to this argument. But anyway, so that's so this suggests that in actuality Elon Musk has said he doesn't want to harm the search for life on Mars. He's said things as to imply that, but then he might do it according to his own judgment, that he doesn't think that what he's doing is going to do any harm to Martian life, and just launch this mission, and based on reading a somewhat superficial reading like the one that I was talking about in that report to NASA, and he concludes that either Mars is sterile. He seems, so far, the only thing I've heard him say is he thinks that the surface of Mars is sterile, and any life would be deep below the surface. So he could launch to Mars still thinking this and not believing anyone who says anything else. And the Outer Space Treaty doesn't seem to give protection against that if you take Laura Montgomery's thing. So she's saying that we would have to have a big legislative thing in the United States to clarify the law. Congress would have to step in and clarify the situation there. And if that is true, and if there was a big space colonization lobby, then you could imagine a situation where Congress clarifies it in the direction of saying that it's okay for Elon Musk to go there. But I don't think that's actually going to happen myself. because the reason is that there's a protection in the backwards direction from Mars back to Earth. So Elon Musk is not a Mars One enthusiast. He doesn't want to just send humans there and they just stay there and they don't come back again. He wants them to at least be some shuttling back and forth. So if you're shuttling back and forth, then you've got the problem that your spaceship, even before the humans land there, the spaceship lands on Mars, and it'd be very difficult for one of these huge what they call it, starship or whatever his things are called, then for one of those to make sure that no Martian dust gets into it, and that it's not contaminated in any way, and even harder to sterilize it before it comes back to Earth. So then, it's given that he wants to shuttle back and forth from Mars, I don't think the space colonization group people are even aware of this issue. I wrote an article about it, but I doubt very many of them have read that. This is my Likely 2040. I'll bring it over here. Likely 2040 before. So this is an article that I wrote about this whole issue, and I mentioned amongst other things this thing that the astronauts coming back from Mars, that they would have to even before the astronauts get their spaceships, would have to be that Earth is protected from spaceships coming back. So so go back to my thing. So I need to explain how we are legally protected in that direction, so that you can understand. So that's a quite natural thing going on to the next stage, sample return. So and now this is just a little thing about NASA. Well, it's not so little really. NASA's attempt to find life on Mars, they have come to the conclusion, completely counter to what all the recent papers by astrobiologists say the only way to search for life on Mars, the only way that makes sense economically, is to search for it in situ on Mars. Because they don't know where it is. I mean, if you're lucky, it's in the very first place you look. But it's very probably it isn't. And you could even, for instance, drill in a rock, and just 10 centimeters away from it, there's the life, but you can't detect it. If you can't detect it in situ, then you're going to just be returning random rocks from the Martian surface. And it could well be that life is really quite sparse there, and you have that in Earth deserts, in the Atacama Desert and various deserts. You have these rocks, and they have these little patches of life, and other parts of the same rock don't have any life, with no real apparent difference. It got there and it didn't get there. Certain microhabitat changes maybe. So without knowing where to look, and it probably involves drilling, and the Curiosity's successor isn't going to be able to drill. ExoMars is, but it isn't. So it wouldn't be able to dig down to this biofilm that I was talking about, for instance. It's just like Curiosity. All it can do is drill little bits into rocks. I don't know if its drill can actually work into sand. So certainly they're only talking about returning samples of rocks. And so it could very well return and tell us absolutely nothing about whether there is any life there, even if there's life, even if it's trundling over life all the time. And on the other hand, if you go to Mars, and if you look at the most interesting Mars meteorites that we have on Earth, so we have meteorites from Mars that have come back here, and they've got very interesting organics in them, and they've got tiny structures that look like cells. And if the Mars 2020 rover were to find one of these meteorites, like ALH 84001, for instance, if they were to find that on Mars, they would target that as being a top priority sample. That would be the very top priority sample from all the detection of organics, and they would conclude this is the very first one we have to return to Earth. And there's some other ones, another Mars meteorite that's even more interesting that we already have. And so astrobiologists say you've got no way of knowing if you can't find life on Mars first, then you're going to be returning samples that are just like the Mars meteorites we have already, and for $10 million per gram, then you're getting things that we could find on Earth by just searching more thoroughly for Mars meteorites. And especially because NASA are not planning to sterilize the sample containers thoroughly. They are going to sterilize them as well as they can, but there's a small probability of a viable spore in one of the sample containers. they're not going to sterilize it enough to be absolutely certain there's no viable Earth spore in it. That was an executive decision they made in their planning stage, because it was just proving too expensive and difficult to sterilize it thoroughly. So they made this executive decision to allow a small possibility of there being a spore in one of these containers. And knowing that most an awful lot of Earth life has not even been sequenced, is hardly well known, then you could easily come to the conclusion that you think what you've got in your sample is a new life form from Mars, when it's actually contamination that you sent up there yourself. So these two reasons why it's a very ill-conceived mission in my view. I can understand astrobiologists not liking to actually speak up publicly, but if you look at their papers, then that's what they say. They say this is not the way to do it. A white paper signed by 8 NASA astrobiologists, and it was considered by the Decadal Review, and this paper was quite clear. They said you're risking mortgaging the future astrobiology on Mars for the small chance of I can't actually remember the actual words, but it's pretty much like someone mortgaging their ranch on a lucky dip. That's basically what NASA are doing with the Mars sample return. On a lucky dip that could have anything from like a bad egg through to $1 million. That's basically what NASA are doing with this sample return, in my view. So I'm not attached to any institution. I'm a software developer, and I just do blog. I'm just a science blogger, so I can feel free to say these strong-worded things. And I know that's provocative, but maybe if some of you are associated with NASA, you might give it some thought. Why are you doing it this way? What's the point? Anyway, and I think that if you now look at how they're going to do these, of course, the sample return would be brilliant for geologists. I don't deny that a bit, but it's very expensive at $10 billion per gram to return samples from Mars. Again, when we have, of course, knowing where it was in situ on Mars and returning it to Earth, then that's very, very good for geology. To say, it was this particular rock, we saw it there in situ, in that connected position. We go and measure the isotopes and things you can do on Earth that you can't do very well on Mars. Although you can measure isotopes in situ in some ways. So anyway, now I'm going to explain how we are well protected. And actually, NASA are not going to be able to return this, because it could actually be quite harmful to humans. So I'll explain why it could be harmful, because I haven't really motivated this. And this is I've been encouraged by an astrobiologist friend to write an article, for an astrobiology journal, and I haven't actually, and it's there. I've actually put a preprint up. If you're interested, you can have a look at the preprint. It's some of it's mid-edit, but it's mostly there. But I wouldn't. The whole thing is rather too long. I think it's 100 pages, 116 pages, so it's quite long. And I'm considering trying to get a small part of it, published with Astrobiology Journal, but I haven't had time to work on it for some months now, and so I've just got it here with the abstract. If you want to have a look, then some of these ideas are there, as properly cited and everything, that sort of thing. So anyway, this is what Carl Sagan, then he put it like this: that on one hand, we can argue that Martian organisms can't cause any serious problem to terrestrial organisms because there's been no biological contact for 4.5 billion years. On the other hand, we could equally well argue that terrestrial organisms have evolved no defences against potential Martian pathogens. And that's the basic discussion argument they all have. And Joshua Lederberg, the same thing. He was the very first, in the late 1950s, who was already concerned about planetary protection. long before anyone else. And the way he put it, a Nobel Prize winning, miss out the word prize, microbiologist and microbe geneticist. And he said that if they ever make it here, will they be totally mystified and defeated by terrestrial metabolism, perhaps even before our immune defences come into play, or will they have a field day in life of our own total naivety? It's the same thing as Sagan said earlier, I think, and it goes into more detail that he talks about how microorganisms make little beside proteins and carbohydrates, and which our immune systems respond to, and Martian life, not adapted to live in a host from Earth, but our immune system's not equipped to deal with totally alien parasites. I mean, for instance, suppose you had a very robust form of RNA world life. It would only have RNA and ribozymes. And would our immune system even notice something like that as being no proteins, and maybe doesn't have the right carbohydrates, and we just wouldn't actually maybe not recognize it as being life at all, and it just gets into our lungs, and maybe for some reason it's not feeble stuff, and it just starts eating our lungs, and our lungs don't even notice that there's anything alien there. And we do have there's Legionnaire's disease, which is a disease of biofilms, which even if it's Earth-related, at least these are biofilms that is also able to. I wish I could switch off notifications. Sorry. There's a disease of biofilms that I know. I'll try and cover that up with. Maybe that'll work. There's a disease of biofilms that called Legionnaire's disease, which is also affects infects our lungs in the same way. And so that's another possibility, that there could be Earth-based biofilms there. They've got diseases of them that would also be diseases of our lungs. And if it's either way, it could well be that our antibiotics just do nothing to protect us against them. So it's very important to be protected, and that's just humans. But it can produce toxic chemicals, and that is just accidentally poisonous to us, like the way cyanobacteria blooms kill cattle and dogs in the Great Lakes. It can be an opportunist local infection like tetanus, which is not adapted to kill humans, attack humans. It could be aspergillus, that's an allergen that causes asthma. And fungi like that kill an estimated 1.5 million people worldwide, and it could well be fungi from Mars that could survive on Earth. Then numerous other ways, and then we go even further. Claudius Gross, he looks at possibly interpenetrating biospheres, and his worst case is scenario. And so please remember, when I say all this, this is not something you need to worry about, because I say we are well protected. I'm just trying to, and I'm hoping to get people, and with my biosphere collisions, I want astrobiologists to start thinking about this, and people to actually start talking about, could it be that we could return something like this? And then with wide awareness of that, then hopefully, because they don't seem, when they talk about planetary protection, I don't see people talking about things quite as dire as this as a possibility. But, except Claudius Gross is the only one that I've seen. And maybe it can get people to wake up and think a little bit more about this. That is really, we don't know. And if you start thinking about it this way, then if you've got a mix of two interpenetrating biospheres, and he was looking about in the forward direction of Earth life going to an alien planet, but it would be the same alien life coming back to Earth if it's reasonably advanced, then you end up with a mix of Earth microbes and alien microbes in almost any habitat, assuming that the other life is as adaptable as ours, and because microbes can evolve very quickly, and you imagine life on Mars is adapted very, very quick, varying temperatures, ionizing radiation, UV. I mean, it's probably going to be absolutely fine in almost any habitat on Earth with a little bit of more adaptation. So wherever you go in your stomach, half of your gut microbes have perchlorates inside instead of salt. And they produce strange biochemicals that make an awful lot of sense on Mars, but Earth life doesn't know anything about it. What's going to happen? I mean, perchlorates are poisonous to humans. And so, as Carl Sagan said, it could be that we need kilograms of Martian life and nothing happens. But it could be that if it can somehow survive in your stomach, I know that's a very unlikely habitat for Martian life to survive, but if it's evolved a bit, then who knows? It now seems that oxygen is not likely to be a problem for Mars life. If there's quite a lot of oxygen habitats there, in any case, it's a very oxygenated, it's a hyper-oxygenated surface with the hydrogen peroxide and the perchlorates. So it's not too likely that the reactivity of the oxygen on Earth makes any difference to Mars life. And in our lungs, on our skins, and harming, and photosynthetic life may be spreading across the oceans. And so he looks at this idea that if you've got, he says that his worst case is that both the Earth and the introduced multicellular life from Earth is reduced to a microbial slush due to the inability of either type of multicellular life to recognize the microbes from the colliding biosphere as non-self. And his is a similar argument to Joshua Lederberg's. He says, how likely is it then that non-self recognition will work also for alien microbes? Here we presume that general evolutionary principles hold, namely that biological defense mechanisms evolve only when the threat is actually present and not just a theoretical possibility. Under this assumption, the outlook for two clashing complex biospheres becomes quite dire. In the best case scenario, the microbes of one of the biospheres will eat it first through the higher multicellular organisms of the other biosphere. Primitive multicellular organisms may, however, survive the onslaught through a strategy involving rapid reproduction and adaptation. The overall extinction rate could perhaps then be kept within, with respective recovery times of 1 to 10 million years. That would be comparable to one of the big terrestrial mass extinction events. He's talking about primitive multicellular organisms, ones with very, very fast reproducing, little multicellular creatures that can reproduce very quickly, so they can adapt quickly. And in the worst case scenario, more or less all multicellular life is eradicated, and it's back to microbial Precambrian state with considerably prolonged recovery times. And the leftovers may coexist in the end in terms of shadow biospheres. This is not impossible. And mind you, again, we are protected, legally protected from all this. We've got so little experience. We don't know how likely. It could be that it's extremely unlikely that there could be even any life on Mars. It could be that it's very likely there's even independently evolved life on Mars. We just don't know enough about our galaxy to know which of those is most likely, whether it's likely to be related, whether it's likely to be unrelated, whether it's likely to be early life, whether it's likely to be late life, whether what actually would happen when two biospheres collide. We don't know. We simply don't know. And I think that astrobiologists often seem to say, it's probably going to be fine when we return it, but we don't absolutely know for sure. I'm not sure that's I think that's going too far. I think that's being too confident even, just even saying there's a small risk. We don't really know there's a small risk. And in one poll of astrobiologists at a conference, then a very informal poll, and there's a wide range of opinions on this as to whether it's how much of a risk it is. But that wide range of opinions, we should, with the precautionary principle, we should certainly take account of the possibility that it could be harmful. So now I want to explain how well we are protected. Because, Margaret Race looked in detail at the legal process would have to be completed to return a sample from Mars to Earth, even to a purpose-built receiving facility. So, before sample return, we have first of all a formal environmental impact statement for NEPA. That is very common. Environmental impact statement. Yes, that's common for space missions. An average length of time for that is about 12 months. It's about 46 months. And then we would have a presidential review of potential large-scale effects on the environment. That's to be done after all the other domestic legislation is completed. And that's something you don't have for current space missions. And alongside that, you have international treaties to be negotiated, you have domestic laws of other countries, and then the various laws that you have to do with the country that's launching as well, you have to look at the full range of worst-case accident scenarios, the Environment Protection Agency, Occupational Health and Safety Administration, because humans can get infected, laws of quarantine, because even though you're not returning humans, you would have humans that are operating the sample returning facility, and you're asking, suppose that they got contaminated while handling a sample, then would you quarantine them there indefinitely if it could last for 20 years before it actually has any symptoms? But it's not just that. Again, with quarantine for these sample returns, people tend to look only at human diseases. But what about a Mars microbe that it actually takes part in your skin colony, just like the possibility we have hydrothermal vent microbes in some people's belly buttons, for instance. So you could have Mars microbes that just get into the colony on your skin or in your belly button, and so on. And you can't sort of wash it off. You can't wash off all the microbes just with only soap. So these microbes then, and you can't sterilize a human being in the way you can sterilize, say, a rock sample. And so this microbe may be completely harmless to a human being, but as soon as the human being gets out and starts walking around after it gets out of their quarantine, and been sitting there, maybe it's in a spore, maybe it's actually able to sort of survive and do things and reproduce on human skin, and then it gets into the environment, and although it was harmless to human beings, maybe it kills dogs. Maybe that seems a bit improbable. Maybe it's harmful to certain kind of insects. Maybe it's able to photosynthesize, and it competes with and it takes equal parts in the ocean, where you've got half Martian plankton and half Earth plankton. And maybe that's not so good for things that eat plankton if half of it is Martian, or maybe in the soil. And you wouldn't know because it didn't do anything to a human being, but because human beings wouldn't be kind of eating it, but it gets into the environment and something else eats it. So I don't think that actually quarantine works. I think that if we'd gone back to the time of Apollo, then I think what we should have done, if we had present-day technology, we would do in-situ searches on Mars first without sending human beings there, despite all the people of wanting to beat Russia to the moon. I think if we had believed, did I explain that Carl Sagan, at the time of Apollo, then he thought that there was a possibility of life a couple of meters below the lunar surface. It's much harsher than what we now think Mars conditions are like, but there's still a very slight possibility before they made the Apollo discoveries that there could have been a habitat of ice well below the surface that was sometimes habitable for lunar microbes, and that was the reason that they did do the planetary protection. So, but if I think the way we should have handled Apollo is that we should have sent robots there to search for life there in situ. It would have been extremely difficult with 1960s technology. We probably couldn't have done it. So it's actually, looking back, it's rather difficult to know how we could have protected Earth back then. And it might be that other extraterrestrials, that if they have moons with other life on it, it's actually harmful to them. They're just not able, they're just too eager and they don't think about this and they go extinct. It could have happened. So I think back then we weren't very well protected at all. But I think we are now, because we understand very much better these sort of things. We've moved forward. We actually are so well aware that things can actually be harmful. And we have ecosystems, even if we don't have other biospheres, we have enough analogies from ecosystems and sending things from. We have even microbes harmful on Earth. For instance, the freshwater lakes in New Zealand, which are being harmed by microbes that come from the northern hemisphere, and they're spreading there, and they got there in divers equipment, and so that shows that even microbes on Earth can be invasive. So anyway, so the quarantine would be affected. We'd have to have new quarantine regulations, but actually I don't really see how quarantine regulations can work to protect Earth in a sample return facility. And certainly all that would have to be gone through. And then apart from that, and the new side, there's the agriculture is affected. It could affect your agriculture, so that's going to be affected. There's going to be There's going to be loads of different bodies going to be involved, many legal laws that we have to protect these different things. They're going to be involved in domestic stage, and she did not estimate a total time for all this legislation to be passed. And as it goes through, then you would find that the new legislation that you hadn't thought of, that you have to navigate as well. You know, maybe it's going through, and then you suddenly realize, oh, we need to look at the effects on agriculture, say. So once it's all sorted out, once that whole process is completed, then we have to make the facility. Now the facility that we have two sample return, each sample return study has got more and more complex with the facility, because they have to design to be able to protect against any conceivable astrobiology. If you don't know what's in it, and remember that's NASA's plan, is to return a sample that could have life in it, and they don't know what's in it. So if you do that way, without looking in situ first, if you look in situ first, you know what's there, and you may know what's there well enough to be able to protect Earth. For instance, you find early RNA world life, and you look at it and you see it's very feeble, it's sharing its RNA freely between different microbes, then you could say, well, okay, we're fine. We don't need to worry about that. We can certainly return it to Earth. But if you don't know what's in it, then you've got to protect against any conceivable extraterrestrial life, when we only have Earth life as an example to go by. And that's extremely difficult. And the first studies thought we just put into a kind of use these gloves into a compartment in an ordinary biosafety, the highest grade of biosafety facilities we have on Earth, biosafety level 4, and just return it inside one of those, and with a kind of compartment, and with using gloves to manipulate it. But then the next one, which was the National Research Council, by then we discovered the ultramicrobacteria, which are only 200 nanometers across. And then people started thinking about that you've got to protect it both ways. You've got to protect the Mars life from Earth microbes contamination, and the Earth, and they also protect Mars life from coming out. And you have this very complex facility, such as we have never built, where you have double protection with some kind of thicker in between. You have this wall that could be pressurized to stop them from coming into it from either way, and continually pressurized. It's quite a complex thing to try and organize to make sure that it can't go either way. And then with the next one, the European Space Foundation, they had first of all realizing that extraterrestrial life could be much smaller than that 200 nanometers. It could be down to 40 or 50 nanometers in diameter. And that was based partly on me examining some material from the late 20th century. I'm not quite sure why the other one didn't cover that, but they looked at that, and then I can't remember the details. Anyway, they looked at they certainly, the other one didn't have that 40 nanometer requirement. This one did. It said that something below 50 nanometers, a particle above 50 nanometers shouldn't be. They had these different sizes, and I think below 50 nanometers, not in any circumstances, and ideally something a particle above 10 nanometers shouldn't be allowed to be removed. This is shouldn't be able to escape from the facility. It was well sub optical resolution that they recommended, and they said that this should be revisited. So it's well since then. So we certainly have to revisit again, and we'd expect quite possibly that they would require more stringent requirements since then. And so anyway, and they said it would take about 7 to 10 years building this facility, in estimates based on that. 2 years it would be operational before the launch. Now, with all this experience of Apollo and the many things that they did wrong, then it's now considered very important that we have the facility actually operational and people actually knowing how to work it before we launch the sample return mission, and 2 to 4 years to collect it and return it. That has an extra 11 to 20 years. And so add that to the 10 years for legal process, we have 21 to 30 years. But the process of building and testing of the facility alone could take 20 years if we go by the upper limits. And so if we wanted to sample return to Earth by 2040, if we start in 2018, it's not at all clear we can do it. We could speed it up by starting building the facility right away and using the European Space Foundation requirements, but NASA won't do that because they require the laws to be already in place before they build the thing according to those laws. And it would certainly be a risk because you build it and then maybe you have to change the design. And so if we do it so the legal process is first, then it's very hard to see how we could have it all finished by 2040. And I just don't think NASA are going to do this. I think all they're going to do if they even do return these samples, I think they're going to sterilize them. Because they haven't even bothered to sterilize it in the forward direction completely of Earth life. It isn't really a very strong focus on astrobiology. I think they're really more interested in the geology. And for the geologists, if you sterilize it with ionizing radiation, then you can take account of that when you analyze it, if you know very well what you've done. So I think they're just going to sterilize it. If they do want to return it unsterilized, they could return it to well above geostationary orbit. That would be a very safe place to return it. I've looked into various places you could turn it. You could turn it to the moon. You can't return it to low Earth orbit because no point in having humans going back and forth. That doesn't work. Because if you've got humans going back and forth, you've got that whole quarantine thing. Quarantine doesn't work. And so I know that is me saying that, but give that some thought. If you think quarantine would work, then try and think how you would get around the issues that I've mentioned. So I think the best place in the Earth system would be well above geostationary orbit, as far away gravitationally from the Moon as the Earth, in a very stable orbit. And I think that if we do discover interesting life on Mars, and I think we should do it in the forward direction, we search in situ for life on Mars, and we use our instruments searching in situ just as the astrobiologists recommend. And then I think once we find interesting life on Mars, I think we should return it to above geostationary orbit. For instance, we could send one of Elon Musk's Starshots spaceships up there. He claims that they're going to be very low cost individually. I think tens of millions or something. I don't know how he thinks he's going to manage that. But if he is right about that, then you just buy one of those and put them up a third of the way to the moon, say, and then you call that your extraterrestrial life handling facility, and then you send everything only one way from Earth to that, and telerobotically controlled instruments. We are already able to do operations telerobotically, operations on humans. So we can certainly do very fine manipulation, especially at such close distances above. In fact, you could by then, we have, if it's late 2020s, who knows, maybe we can have a spaceship up there with humans, sort of a thousand kilometers away, operating instruments by telerobotics. So if it is very dangerous life, if we find there's life on Mars that would damage our lungs, then I think we should do something like that. And that would be the way to find out. But I think we should search in situ on Mars first. Anyway, but the whole point in all this, what I was saying about this NASA report, is that that we are protected by this, and these are very robust laws. And it doesn't matter what they do with the Outer Space Treaty. They could categorize it, category 2. They can say it's the same as the Moon according to the Outer Space Treaty. But this is nothing to do with the Outer Space Treaty. This is all based on you would have all these laws, the formal impact assessments. This legal basis of these are bulletproof laws that we have on the Earth to protect the environment of Earth. And based on those laws, and everything would be done in the open with public consultation. That's another thing that Margaret Race came to. That it would be a very public thing, and everybody would be discussing it, and it wouldn't just be the space colonization enthusiasts. And the space colonization enthusiasts, they sometimes motivate this by saying, well, we must take risks because we've got to find another planet to live on in order to, as a kind of safety for Earth in case we become extinct on Earth. And there's absolutely no risk of extinction from climate change if you're worried about that. And I've actually been through, I help reassure these people who are worried about various ways that humans could be harmed. And about the only one that is really kind of makes a lot of sense. Well, there is, even the very worst case, if we were to return as life from another planet, we have much better ways we could survive. But this is not a pleasant future, and as I say, this is not going to happen. But you could even survive that by having habitats in which you keep the Martian life out of it, and human beings live inside these habitats. Much simpler than a space habitat. But and so it wouldn't actually turn into a complete microbial marsh. It would only be a microbial marsh outside the habitats, and you gradually reclaim more and more of the Earth's surface to Earth life, if in that very, very worst case. But that's not going to happen. It's not going to happen because we are protected. And so where I've got to, that so the she looked at the legal. Oh, I've lost my train of thought a little bit now. But so in the forward direction, yes. Let me just think a bit. Anyway, I've said rather a lot, so it's probably not too bad to have a little bit of a pause at this point. I know, I'll just stop at this point. I know I'm mid-sentence. I see it's 1.5 hours. I'll stop this, and then I'll continue a little bit more talking in a new recording.